Forces allow us to move, and they allow things to move. Without a force, you can't ever get anything to go anywhere. And so this kid in the picture, he's riding his scooter and he's popping a trick, and in order to do this trick, he has to apply forces and overcome some forces. So first off, we've got the force of gravity, which is pulling him down. We have the force of air resistance, which is probably slowing him down just a little bit as he flies through the air. And then if he wants his scooter to kind of spin around or do something cool in the air, he has to apply another force to the actual scooter itself to get it to spin around. And so there's always, every situation in movement or even just standing objects on Earth are always going to have some sort of forces pushing on them. And so in this video we'll define what a force is, we'll relate it to motion a little bit more deeply, we'll talk about the unit for force and how it's measured numerically, and then we'll explain these arrows a little bit more with some vector arrows, vector diagrams. By definition, a force is a push or a pull. It's a push or a pull. And many objects, you could push or pull them to get them to move. In a situation of a football player tackling somebody, you could tackle somebody by pushing them down, by hitting them straight on, or you can kind of come up behind somebody and pull them down. And so in many scenarios, you can push and pull. They're all considered forces. Those are forces that you apply, but there's also forces that are sort of like done from a distance, you know, that you're not necessarily touching something. And so, for example, these guys jumping out of a plane, they're skydiving and they're parachuting out. They jump out of the plane and gravity, you know, from a distance pulls them down. Now, a fun question, I always take these situations and I think, what would happen if there was no gravity in this situation? If this guy jumped out of the plane and there was no gravity, what would happen? If you guessed that he would fly forward and not go down, you're correct, because with no force of gravity pulling him down, he's just going to jump and fly in whatever direction he jumped, which is kind of crazy. He would just fly forward. And then this wrench here, my last example, is just if you want to unscrew something, you have to apply a force to the wrench. If you don't apply a force to it, a push or a pull, it's not going to unscrew. You need to apply force. So overall, when we talk about forces, we're going to talk about just the basic forces of motion that cause things to move. Things like gravity, friction, tension, and applied forces that we would apply or a machine applies. I mentioned that forces cause movement, they cause motion, but what if I want to sort of control that motion a little bit more? Like, let's say I'm playing a sport and I want to knock a guy down in a football game. I want to tackle him, but he's a lot bigger than me. Well, what do I have to do to tackle that big lineman? He's got way more mass than I do. I probably can accelerate faster than him, so what do I have to do? Well, look no further than to Newton's second law, which relates force, mass, and acceleration together. And if you want to match his force, like he's coming at you at a certain speed, the lineman, and you have to tackle him, how much force do you need to take him down? Well, if his mass is like twice as much as you, like let's say he's 100 kilograms and you're like 50, well, that means you're going to have twice as much acceleration to take him down. You're going to have to move faster. And so, I always tell the little guys, don't shy away in a game because the guy's bigger than you. You have to use your speed to your advantage to match his force. And so if you can come head to head on that, you can take down the big guys just by using your speed. So that was football. Let's move over to the skydiver picture again. I want to illustrate one point, and that is for applied forces. Sometimes in like football and sports with volleyball, you hit something like a baseball or volleyball and it's over. You've applied your force and it's done. But some forces are continuous. Like gravity is a continuous force that's always on us as long as we're on a planet. And so when a person jumps out of a plane like this, that force of gravity is continuously applied to them and continuously accelerates them towards the ground, and it kind of keeps adding up. And so like if you jump out of a plane, the acceleration of gravity, just a random number that you guys should probably kind of store in your brain, is 9.8 meters per second squared. And what that means is that every second you are accelerating 9.8 meters per second. So after 1 second, you would be going 9.8 meters per second. And then after 2 seconds, you would be going 19.6 meters per second. And you can kind of do the math on that. After a few seconds, you're going to be going really, really, really fast. And eventually, the force of air resistance slows you down and you reach your terminal velocity when those forces balance out. But I just want to illustrate the point that some forces are applied and they kind of are over and done with after they're applied, but some forces are continuous, like gravity. So what's the terminology for force? If I want to actually quantify how much force I'm putting on something or someone, or how much a machine is putting on something or someone, what do I call it? Well, you measure all forces in newtons, and by definition, write this down, a newton is the force needed to cause a mass of 1 kilogram to accelerate at a rate of 1 meter per second squared. All right? That's what a newton is equal to. 1 kilogram accelerating that 1 little kilogram to 1 meters per second squared. Where did this unit come from? Well, by the one and only Sir Isaac Newton. He's a very famous scientist, famous for his laws about motion and gravity. So, you know, the holy grail of all scientists, you get a unit named after you. It's pretty awesome. In addition to putting numbers on forces and calculating them using like F equals ma, it's also really helpful to know where they're coming from, because if we know where they're coming from, we can predict motion and we can kind of see why things move the way they do. That helps us build buildings, because we know what forces are acting on the pillars and the supports, and the sheer wind speed, designing buildings for earthquakes. You know, there's a lot of forces involved with everything that we build. Same thing with machines and cars, knowing the stress that needs to be put on the suspension, the stress inside the engine, the forces involved. There's so many different things, even in our bodies. You know, like I watched this video of a guy who was free running. It's such a cool sport where they pretty much like jump off buildings and they are unharmed. Like the dude jumps off a 20-foot building and he's like rolls and he's like, oh yeah, no big deal. I mean, I'd jump off a 20-foot building and like hurt myself. I'd break both my legs probably. But he jumps no problem. And so that person has a great understanding of force. He knows how to sort of manipulate force, so when he hits the ground, he rolls a certain way so that the force is mitigated and it doesn't hurt him. But anyway, there are two kinds of forces, sort of, or two kind of ways to categorize forces when they're interacting with each other. If you have two forces interacting with each other, they can either be an unbalanced force or a balanced force. And so this diagram is perfect right here on the top. This first one is if you have force A and force B, and you were to add them together, you would end up getting like a really long arrow because they're all going in one direction. It's an unbalanced force. It's going to cause an object to move. Unbalanced forces always cause objects to move. Write that down. Unbalanced forces cause objects to move. Now, on the other hand, a balanced force is going to cause an object to stay still. And so you've got force A and force B in the second one right here. And that one is going to pretty much like add up to nothing. If you have these two forces going against each other, they cancel each other out, and the net force is 0 newtons, and you just don't get any movement. And so I have pictures here that show both of these. The first one is an unbalanced force. You have the force of the propulsion, which is pushing up hardcore. Like it's a huge force, tons of energy coming out of the bottom, pushing it up. And then you have the force of gravity, which is pulling down. And when you kind of add those two arrows up together, this bottom arrow is obviously much bigger than the top arrow. And so that's an unbalanced force. Because it's unbalanced, the rocket can actually go up. Now, if you didn't have enough propulsion there, then it wouldn't be able to overcome the force of gravity, and it just wouldn't work. My example of a balanced force is this standing yellow mongoose and the Golden Gate Bridge. Because both of these things are still. They're not moving, they're standing still. There are still forces acting on them. You still have the force of gravity, which is pulling down on the marmot, but then you have the force of the ground, which is pushing back up to keep him still. Not marmot, mongoose, my bad. I just saw it and I was like, perfect picture, that's great. Same thing with the bridge. Gravity is pushing down on the bridge, and then the force of the ground is pushing back up. We'll talk about these free body diagrams a little bit more. We'll do lots more examples, but overall, I hope you guys understand the concept of force a little bit. You understand forces are pushes and pulls. You know what the SI unit for force is. And you understand kind of how to draw forces in using arrows. Take care. It's time to go to fourth period.